Here are solutions to homework set number 8 for ECE 376. This homework set looks at timer 2 interrupts. The first problem is to build an egg timer, kind of quick egg timer. So what I want is this. I'm going to measure time to 0.1 millisecond. When I hit RB0, I initialize the time to 5 seconds. Then it counts down to 0, stops at 0. This starts at 10 seconds, 15, and 20. So how do I do that using timer 2 interrupts? Well, the first thing is I need to set up timer 2 for 0.1 millisecond. For that, n equals 1000, and a combination of A, B, and C that does that is 10 times 4 times 25, which means that T2 con should be 4D. So this is the field for A. That's 9. 9 means 10. Here's the field for C. 0, 1 means 4. And this is the timer 2 enable. Splitting it up into nibbles gives you 4, 13, which is D. And then PR2 is 24, meaning 25. So there's the timer 2 initialization. The counts that I need to initialize, I'm going to decrement to 0, stop at 0. 5 seconds is 50,000 counts at 100 microseconds per count. There's 10 seconds, 15, and 20. So these need to be long integers to store numbers that large. Let's look at the code. So here's what the code looks like. Again, setting up, don't really care. Here's the interrupt service routine. I'm going to toggle port A pin 1. That lets me measure the frequency, checking that timer 2 really is running at 0.1 milliseconds. I should see 5 kilohertz on RA1. I'll decrement to 0, stop at 0. Anything that's 0 is false, anything non-zero is true. So anything that's not 0 gets decremented. And then check the buttons. If you hit a button, that'll initialize the counters. This turns on timer 2 for 0.1 millisecond, and the main routine, all it does is display. So all said and done, what I wind up with is code when I compile it is 2622 bytes, or 1,311 lines of assembly. If I measure the signal on port A pin 1 is 5 kilohertz, saying that timer 2 is running at 100 microseconds. That's correct. And when I hit the button, that initializes my counter. So there's 20. And I got the code set up that it won't recognize the button until you get to 0. Decrement to 0, stop at 0. So that's problem 1. With timer 2 interrupts, you can measure time. A second thing you can do with timer 2 interrupt, you can output a precise frequency. So for example here, I have a 1-key piano. It plays one note, 174.61 Hertz. When I hit RB0, you can play your one note, and with that you can listen to your talking head songs. Burning down the house. So, great fun. How do you output a precise frequency? Well, to do that, I need to know the number of clocks between interrupts. That's 10 million divided by 2 times Hertz. 28,635.244. Come up with some combination of A, B, and C that does that, with the limitations that A is a number between 1 and 16, C is 1, 4, or 16, and B is a number between 1 and 256. One combination, kind of using iterative search, trying to figure out which one's close. 10 times 16 times 179 is close. B should really be 178.97, rounded to 179. That's not too bad. One combination. To do that, A is 10, meaning this field is 9. 9 means 10. C is 16, so this field is 1, 1. There's your timer 2 enable. Splitting into nibbles, this is binary 4, binary 16, or F. So I'm going to write 4F to T2 con, 178 to PR2, that gives you 179. If I do that, there's my frequency. From a frequency counter, that's 174.5 Hertz. It's supposed to be 174.61. You're pretty close. Again, I can't get exact, I can't do fractions. I'm off by 0.03. Not too bad. The resulting program is 1204 bytes, or 602 lines of assembly. And what the code looks like, the part that you really care about is right here. Here's the interrupt service routine. If I hit RB0, I toggle port A pin 2. I always toggle port A pin 1, and I do that just for measuring frequency. It's always outputting a square wave. I can always measure that. Yeah, don't care, don't care, don't care. Here's the timer 2 initialization. That sets up timer 2 for 174.61 Hertz. Then the main routine doesn't actually do anything. It just counts on port C. So down here, you see port C counting. That doesn't have anything to do with the program actually. It's just counting, showing that the program is running. The interrupts are doing all the work. Next problem. Next problem is build a reflex timer. So here's what I want. I'm going to press RB0. When I do that, between 3 and 7 seconds later, these lights come on. When they come on, I hit RB0, and the time delay between when the lights came on and I hit the button is displayed. So let's try that. I hit RB0. This light comes on, telling me that the counter is starting. Between 3 and 7 seconds later, 1, 2, 3, 4 seconds after they came on, I hit the button. And that says my reflex was 4.184 seconds. Try that again. Let's make it 10 seconds after the light comes on. Right now I'm just checking to see how accurate the code is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, not too bad. Okay, now let's do my reflex time. I'll hit the button as soon as the lights come on. Okay, that wasn't very good. I got distracted. Try that again. Watching, watching, watching. Better. That measures your reflex time. So how do I do that with timer 2? Well, the first thing you need is a flowchart. What I'm going to do in the main routine is I'll initialize port B to input. That's my start and stop button. A, B, and D is output. Set timer 2 to 0.1 millisecond. Actually, this code is 1 millisecond. Okay. I'll wait for RB0. When I press it, generate a random number between 30 and 70, meaning 3 to 7 seconds. Wait that amount of time. I'll then turn on the lights, initialize my timer to 0, wait for the button to be pushed. Once it's pushed, record the time that's elapsed, and display it. In the background, timer 2 is running. Increments time, that's all it does. The resulting code is 2818 bytes, or 1,409 lines of assembly. The timer 2 interrupt. All it does is toggle RC0. That way I can measure the frequency to make sure it is interrupting at the right rate. Increment time. Timer 2 I set up for 1 millisecond. Then in the main routine, I'm going to clear port A, wait for you to hit the button. Once you hit the button, I'll turn on port E pin 0. That's the light over here, just to tell me that the timer is running. I then wait for me to release the button. While I'm waiting, I'm counting mod 4000. That's your 3 to 7 seconds with a resolution of 1 millisecond. Once I release the button, that's my delay. It's a number between 1 and 4000, plus 3000 gives you a delay between 3 and 7 seconds, 3000 to 7000 milliseconds. I'll turn on port A, clear my timer, and then wait. Wait till I hit the button. Once I hit it, I'll record the time, and that's my reflex time. So when I try that, I'll hit the button. Lights turn off. I'll try that again. Hit the button. RE1 turns on. There's my timer. 3 to 7 seconds later, the light comes on. Hit the button. That was 1.554 seconds later. Problem 5. Collect some data. So I'm interrupting at 1 millisecond. I should see 500 hertz on RC0, and I do. So timer 2 is working correctly. Collect some data on my reflex time. I took 4 measurements. That's what I got. Had a pretty good day. With that, I can do some statistics. My data has a mean, has a standard deviation. The mean is 170 milliseconds. The standard deviation is 2.6. So my 90% confidence interval, where this is 90%, is the mean plus or minus 2.35 standard deviations. Where this comes from is the t-table. I've got 3 degrees of freedom, sample size of 4. I want 5% tails. To do that, I need to go left and right 2.35 standard deviations. So 90% of the time, my reflex will be between 176 and 164 milliseconds. The probability that my reaction time will be less than 200 milliseconds is, here's the number 200. I want to find that distance in terms of standard deviations. That's my t-score. That's 11.12 standard deviations away. So this area is 99.8%. This area is 0.2%. Problem 7. Change something. In this case, I went off to class, came back about an hour later, took the test again. So here's my reaction time. Is there a difference in the two distributions? So I've got my 2 populations. Here's population A, here's population B. A had a mean that I forgot of 170. B has a mean of 194. To see if there's a difference, what I do is take create a new variable W. That's the difference between the two. The mean of W is the mean of A minus mean of B. The standard deviation of W is the square root of the variance of A plus the variance of B. The t-score, here's what W looks like. Mean is minus 23. So 0 is way over here. The t-score is how far is 0 from the mean in terms of standard deviations. It's 1.79 standard deviations away. From a t-table or a stat track, what that tells me is that this area is 8%. This area is 92%. So 92% chance my reactions got less after going, or got worse after going to class. Whatever that tells you. That's for an individual. This way, just run one more experiment. If I want to know, is my overall reaction time getting worse? That's a population question. For populations, you divide by the sample size, divide the variance by the sample size. Now my t-score is 3.5, meaning 1.8% chance, or 98.2% chance my reaction time gets worse after class. So that is homework set number 8 for 376.